All right, so here are some problems out of Beard Johnson. Um, these appear to be the same, almost the same problem. Yeah. Now, this is not an accelerometer, so we're going to use the vibrometer equation, which is going to look like Z is equal to Y times, and this is the main difference, is that R squared over there, square root of 1 minus R squared squared plus 2 squiggle R squared. All right, so let's read the problem. A vibrometer used to measure the amplitude of vibrations consists essentially of a box containing a mass spring system with a known natural frequency of 120 hertz. Right, so the natural frequency of this is, my N should be a subscript, 120 hertz. The box is rigidly attached to the surface right here, and that is moving according to this equation right there. If the amplitude Zm of the motion, so that's going to be this guy right there that we're measuring, mass relative to the box is used as a measure of the amplitude, determine the percentage error when the frequency of the vibration is 600 hertz. Okay, so a couple things to start with, notably that there's no damping here, so there's no damping. So that guy is going to go away right there, that term. And a little bit more finagling here, not much, but a little bit, a little bit. We get R squared over 1 minus R squared. For this problem, our R, we don't have to convert it to radians per second because we're comparing the two things. We're going to have 600, so it's going to be the forcing over the natural. So the forced is 600 hertz over the natural frequency of 120 hertz, and we get a 5, which is good because we want to have, as we mentioned up above, we want an error term that's like in this range right here. But notably, 0 doesn't do a great job, right? So that's going to be, on this one, it's a gray line. It says undamped. You can see here's the gray line that's moving. It's right around, but it's, I actually don't even show my graph going up past 5, but hopefully it's a flat line and the error isn't great right around there. Okay, so let's stick this into the equation up above and find it out. Take a z over y, which is going to be an error term, but we're going to subtract it. We're going to subtract 1 from it. We're going to have 5 squared over 1 minus 5 squared. So it's not going to be a lot of a difference. 1.04167. I got more X's. It figs. So the error in part A is going to be equal to 4.17%. Now we want to go backwards and see what is going to be at what frequency is the error equal to 0? All right, so we go 1 is equal to r squared over 1 minus r squared. This is the absolute value, by the way. Make sure we have right there. So we have like 1 minus r squared equals r squared for an error of 0. And if you break that up apart right there, you end up with the r squared is equal to 1/2, right? And therefore r is equal to 0.7071. So if you take and use the same idea from up here, we'll say that the forcing frequency is equal to R times Fn. So 0.7071 times 120 you would say that the forcing frequency is equal to for when the error is 0 is 84.85 hertz. And that's basically when this curve up here, ways back, where that gray line here crosses over 1. It's going to be a ways out, right? Because we're looking at 5, or no, excuse me. Let me put it another way. No. What were we looking at? Let me take that back. We have 0.707 says that says where it's crossing. It doesn't seem like it's true to me. 0.707. So that's going to be like, oh, like right there. Okay. Yes, that's what that means, by the way. So that this never crossed. I take that back. I was pretty. I should have known better. This gray line never gets to 1 right there, but it did cross 1 right here at approximately 0.707 right there. I might take this. I have. Let's use this as another problem. So let's end this one, and I'll make another video for the second part.